Okay, we're going to talk about LaPlace transforms now and what they're good for, what they do, and how they work. Now, all the stuff we've been doing has been with periodic waveforms, and we've learned techniques to solve for circuits that have periodicity, a sine wave, and so forth. What we're going to do now is we're going to have a circuit and assume it's reached steady state before a switch is thrown, and then the state of the circuit valid at that point, and that's your boundary conditions. And so you get your initial conditions, and then figure out what the circuit does after t equals 0. You're going to have a differential equation or an integral equation or some mixture. Convert it to algebra using LaPlace. Solve the algebra equation, and then do an inverse LaPlace transformation. So we're going to start with the math a lot, and then more applications, and then this is what we're going to do for the rest of the semester. That's it. This is the last one, last topic. So this is the definition of a LaPlace transform. You take some function f and you multiply it by e to the negative st. Now earlier I said s was equal to j omega. Now we're going to modify it. Back then it was true that s was j omega. We're going to allow a real part to s now. We're going to change that. If s is strictly j omega, that's a Fourier transform. It's a special case of the LaPlace transform. Okay, and for t, we want a solution for f of the function itself is 0 for t less than 0. You'll notice the lower bounds of the integral are 0. Okay, and this just says you got to make sure the integral is bounded, that it will converge on some finite number. The inverse transform, you'll notice that we use capital F for the transform function, little f for the untransformed function. The inverse LaPlace transform acts on capital F and yields little f. And this is the reverse. Now, like I said, in practice, what people do is they have a table of inverse transforms. They don't actually do this integral. They this is like third, fourth year math here, and this is difficult. This is calculus, but it's still difficult enough. So what people do is they use a table, and they use a table of the commonly used transforms. And for that reason, it becomes a useful technique, because they convert a differential equation to algebra, do the algebra, and then convert it back. So, a step function, what does that look like? So we have f of t equals, u is the heavy side step function. To do our step, it steps up, boom, it goes up. To make a square wave, you have a minus u, you'll notice. So we can use this step to build other functions. And for anything arbitrary, we can approximate that with a series of steps. So this can be very powerful. You can just keep going and going. The impulse function, delta function, where you have a very short-term event. Lightning is a good example. In material science, it'd be impact, a shock, etc. The representation, this is only true for the representation. It's not true for the function itself. The function itself is infinitely high. It only exists in an infinitesimally small width. So you can think of it as a square wave. The area is, it's like charge, a current, that when you put current into something, if the current comes in a very short period of time, very fast, you put a certain amount of charge. You can model it as a square wave, a triangular pulse, a Gaussian pulse, etc. But the charge delivered is the same. The current, the peak current, may be different depending upon the shape or some arbitrary shape. All you know is that the integral is some constant. Okay. So this is a sampling. This will sample an impulse. Laplace transform of that is given here. Okay. If t, you have to integrate this by parts. So the function this time is just t, a linear, just t. Integrate by parts. So there, here's a table. So using a similar process, we have a lot of identities that scalar multiplication, you just multiply the transform, addition or subtraction, add or subtract, scalar, working with things on scalars. If you have a scalar times a time scaling, then the transform looks like this. And here's time shifting. This is a step function. You can shift it so that the function doesn't start until t0. So you try to integrate t from 0 to something, and the step function actually doesn't step up until t0. So these are things you can use to shift. And this is what happens to the transform if you do that. Frequency shifting, there's that. Differentiation, you have this formula here. Multiplication by t, you get this, and so forth. T to the nth, there we go. Division, there we go. The integral, and we haven't defined lambda yet. I don't see where lambda is defined. It is some sort of t0, evidently. Okay, convolution. Last one, convolution. So here's a table. This tells you what they call it, names for the various things. So when do you get the Laplace transform of an exponential function? So here's the transform part of it. Here's little f right here. and you integrate it and you get, so the transform of that is right here. Here's some basics, the basic transforms. We've already seen a lot of these properties. We can get the cosine of, get the transform of the cosine as well. This uses Euler's identity, and we get this result. See, yeah, okay, and then we go look up on the table what the transform of negative j omega t is, and we get, we can write it down. There it is. Let's see, did we have the transform of e? There it is. There's the transform of e, of the exponential. A then becomes j omega, and you just plug and play. Whatever a is, j omega goes down here. I'm going to stop this video right here. I haven't, well, wait a minute. Let me go see the next slide. More entries for the table. I'm going to go just a little bit further. And then I'm going to, so now I'm going to stop. And I'll just do this example. Just how do you use this LaPlace transform thing?